Hello everyone. First, I'm going to introduce myself and my team members. My name is Khul Mohammed, and here are my group members: Abdulmajid Gele, Melvin Chi, Nasirul Himam, and Nurul Nadra. And today we are going to present to you experiment 3, which is a vapor compression refrigeration. To begin with the abstract, a refrigerator is a device that removes heat from a low temperature region. Because energy cannot be destroyed, heat absorbed at a low temperature must be released into the environment. So the second law of thermodynamics states that heat will not pass from a cold region to a warm one without the aid of an external agent. Therefore, a refrigerator will require this external agent or energy input of its operation. In vapor compression refrigeration system, a gas is simultaneously compressed and expanded and goes from a liquid into the vapor state. The following diagram shows the basic components of refrigeration system. And here are the 4 basic components of the vapor compression refrigeration system: evaporator, compressor, condenser, throttle valve. Objective: the objective is to determine the vapor compression cooling system's coefficient of performance (COP). And then the introduction. The transfer of heat from a low temperature medium to a high temperature one requires special device called refrigerators. The working fluid in the refrigerators, which is a cold refrigerant, enters the compressor's vapor and is compressed to the condenser pressure. It then leaves the compressor at a relatively high temperature and cools down, and condenses as it flows through the coils of the condenser by rejecting heat to surrounding media. It enters a capillary tube where its pressure and temperature drop dramatically due to throttling effects. Then the low temperature refrigerant then enters the evaporator, where it evaporates by absorbing heat from the refrigerated space. The cycle is completed as a refrigerant leaves the evaporator and re-enters the compressor. And finally, the theory. The cooling system absorbs heat from a low temperature areas and transfers it to high temperature areas. According to the second law of thermodynamics states, the heat will not pass from a cold region to a warm one without the aid of an external agent. The device that applies this process is the refrigerator. And that's all from me, and I will pass to the next presenter.
Hello, Assalamualaikum. My name is Nurul Najwa binti Zukairi, and I will be presenting about the apparatus and methodology in this experiment. So for the apparatus, we'll be using the refrigeration cycle demonstration unit. So the compartment that you need to know, which are evaporator, condenser, compressor, valve, main switch, temperature indicator, and temperature selector switch. For methodology, there will be several steps followed by the figure in order to get you understand more easily. So step 1, the valve was opened and the water pipe was turned on. Step 2, the water flow to the evaporator and condenser that was set up at the rate of 26 grams per second. Step 3, the device was switched on. Step 4, the cooling system was allowed to be stable approximately 10 minutes. Step 5, the reading of temperature 1, temperature 2, temperature 3 and temperature 4 was recorded by adjusting temperature selected switch. Step 6, the reading at temperature indicator was taken. Step 7. The reading of pressure gauge of condenser and pressure gauge of the evaporator was taken. Step, Step 8. The reading of temperature 5, temperature 6 and temperature 7 was recorded manually. Each of the temperature has different place as shown in the figure. Step 9. The experiment was repeated by changing the flow rate of water condenser between 26 to 4 grams per second. Step 10. The experiment was repeated by 4 sets. Step 11. After the experiment was done, that device was checked by closed in accordance to the procedure. Step 11. The flow rate of condenser and evaporator was set up to 0. Step 12. The lamp switch was switched off. After 1 minute, the water supply part was turned off too. And the last step, which is step 13, after 1 minute, the valve will close to the shutdown position. That's all for the methodology for this experiment. I will pass to the next presenter.
Hello everyone, have a good time. We here group 2 experiment 3. In this experiment of Thermo-Material-Lab, today we present in here. So as we have seen the slide, it is the result, which we have the data in here, heat capacity of water, and the table in here. We have seen all the table. We got the heat transfer evaporator and the rate of heat transfer condenser and the coefficient of performance, which we have in here all. And we have also the all 7 temperatures, and the table is in here and the table 1 in here. So we made the calculations and we got the all in here, heat transfer at condenser and heat transfer at evaporator, and the coefficient of performance. So after that we got the result of them in here also, as we see in the calculation is all in here. And then we got the graph. We have seen the temperature is in here, all of them. So we made in here all of them. So the result in here. So that's it, and thank you very much, all of you.
So hi everyone, my name is Melvin Chi. So for my part, I will discuss about the discussion. And for the first question is calculate the rate of heat transfer that occur in the evaporator and condenser for the 5 test run and discuss the result. So without waste any time, we go through first for the rate of heat transfer at the evaporator, which we put the symbol as QL, and the unit is kilowatt. So we given the data for ml is equal to 19 gram per second, and this 90 gram per second we need to change it to 0.01 0.019 kilogram per second. So we also been given this equation, which is QL equal to m delta H, where m is this one, where m is the mass flow rate, while the delta H is the change of enthalpy. So for the test one, which is QL1, which we put the test one as QL1, then we just sub the data for ml, which is the 0.019 kilogram per second. And for the H and H1, first I need to clarify first that H1 and H2 and H1 can be found from the steam table, and the data is we can find the data by interpolating the value from the steam table, and we will get this value. So by that we just sub the data inside this equation, and we will get for QL1 is 46.23 kilogram per kilojoule per second. For QL2, we get the value is 46.21 kilojoule per second. For QL3, we get the value is 46.18 kilojoule per second. For QL4, the value that we get is 46.12 kilojoule per second. For QL5, we get 46.09 kilojoule per second. Like I said before that the QL unit is kilowatt per second. So I just want you guys to know that 1 kilojoule per second is equivalent to 1 kilowatt. So basically all these answer we can uh, equivalent to kilowatt. For example, like this 46.09 kilojoule per second, we also can write it as 46.09 kilowatt. Okay, so next we move to the rate of heat transfer at the condenser, and we put the symbol for condenser is QH, and the units is also kilowatt per second. And the formula is not there is no change for the formula. The only change is the symbol for the Q. Okay. But there for the mass flow rate for the rate heat transfer at the condenser is a bit tricky because each mass flow rate for each experiment is different. As you can see here, for experiment test 1, the mass flow rate is 0.018 kilogram per second. For test 2 is 0.016. For test 3 is 0.012. Uh, test 4 is 0.008, while for test 5 is 0.004. So it's same as before. We just sub all the data inside this equation, and we get for QH1 is equal to negative 43.66 kilojoule per second, and also we kilojoule per second also we I said before that 1 kilojoule per second equal to 1 kilowatt. So basically the answer is negative 43.66 kilowatt. For QH2, the value for QH2 is negative 38.67 kilowatt. For QH3, the value for QH3 is negative 28.95 kilowatt. For QH4, the value for QH4 is negative 19.27 kilowatt. For the last test, which is QH5, the value is negative 9.60 kilowatt. Okay, so next we're going to calculate the coefficient of performance, which is COP. So we so we're going to use the data that we calculate before, which is the QL and QH in this calculation. So for the COP for refrigerator one is we just sub the that value, and we get that the COP for the refrigerator one is 0.514. For COP for refrigerator 2 is 0.544. For COP for refrigerator 3 is 0.615. For COP refrigerator 4, we get the value is 0.705. And for the last refrigerator, which is COP R5, we get the value is 0.828. So from this calculation, we can conclude that the value of this coefficient performance COP is increased linearly with the value of the rate of evaporator, which is the QL. So this is proven in the equation. Uh, so therefore, we can conclude that the coefficient of performance COP is directly proportional to the rate of transfer of heat in the evaporator. So next, I move to the second question under discussion, which is explain the effect of changing the condenser flow rate of T1 to T6 to the compressor power, and draw the graph and discuss the result obtained. So as you can see here, this is the graph that's been drawn, this is the graph of T1 to T6 versus the flow rate in the condenser. And as you can see in this graph, there is a various of color in it. and each color is represent a uh, different temperature. So from the graph, we can see uh, we can see that uh, only temperature path is the graph for temperature path is different from the other. Uh, and as we know that uh, the the temperature the temperature increase while the flow rate in the condenser is decreasing, and by that we can conclude uh, uh, so the statement only valid for temperature 1 to temperature 6 to temperature 7, but temperature 5 did not valid for the statement. This is because I think there is some error that occur during the experiment when doing the experiment. So I think that's it from my part, and I will pass to the next team member to explain his part. So that's it. Thank you.
Okay, as a conclusion, the flow rate in the condense is directly proportional to the compression power. In addition, the coefficient of performance is directly proportional to the rate of heat transfer in evaporator. When the condenser flow rate is increased, the work in input and heat transfer in vapor are increased as well. Furthermore, the condenser flow rate are inversely proportional to the temperature. Okay, that's all for the conclusion. Okay, thank you.